Let's just dive right in and demystify this 6th grade expressions unit, but we're going to do it by treating it like a brand new language. You know, when you think about algebra, it can honestly feel a bit like staring at some ancient foreign text, right? Just full of strange symbols and floating numbers. But here's the real secret. It's literally just a system for communicating logic. So today, we're cracking the code. We're going to start with the most basic alphabet of math and work our way all the way up to translating complex, real-world sentences into elegant algebraic expressions.
So, here's our roadmap for this explainer. 1. Building blocks, understanding exponents. 2. The rulebook, order of operations. 3. Evaluating variables and expressions. 4. Math shortcuts, operation properties. 5. Combining terms and distributing. And finally, 6. Translating the math language. It's a straight shot from the basic alphabet to full fluency.
Okay, part 1, building blocks, understanding exponents. We're kicking off our linguistic journey by defining the absolute raw materials of our new math language, exponents and bases.
So the absolutely crucial thing to remember here is that a base is your primary number, and that tiny little exponent floating above it, well, that's the boss. It tells the base exactly how many times to multiply by itself. Imagine you see a large 9 with a tiny 2 floating up to the right. That 9 is the base. It's doing the heavy lifting. The little 2 is the exponent, just bossing it around, instructing that 9 to multiply by itself twice. So you aren't doing 9 times 2, you are doing 9 times 9. It's just a super fast, compact way to write out repeated multiplication.
Now, what's really fascinating here is how we can express the exact same mathematical thought in 3 completely distinct dialects: exponent, expanded, and standard form. Exponent form, like 5 to the 3rd power, is your quick shorthand. But if we want to see the actual mechanics of it, we stretch it out into expanded form, which is 5 times 5 times 5. And finally, when we actually just sit down and do the math, 5 times 5 is 25, times 5 again, we end up with 125. That's our standard form. Being truly fluent in algebra means you can seamlessly translate between these 3 forms depending on whatever the problem throws at you.
Moving on to part 2, the rulebook, order of operations. You know how grammar dictates how a sentence is read so you don't get totally confused? Well, our math language has a very strict rulebook to ensure we all calculate the exact same answer. Let's actually see why this rulebook is so incredibly important. Take a look at a complex mathematical sentence that seems like it could literally be read in a dozen different directions. Imagine an equation like 36 divided by 3. Plus, open parentheses, 3 squared times 2, close parentheses. If you just read that left to right like a normal paperback book, you divide, then add, then square, and you'd end up with a completely wildly incorrect answer. We really need a systematic way to process all this information.
And to solve it correctly, we use the PEMDAS or GEMDAS process. We step systematically through grouping, exponents, multiply or divide, and finally add or subtract. So going back to that last example, we look for grouping first. Those are our parentheses. Inside them, we have an exponent, 3 squared, which becomes 9. Then we multiply that 9 by 2, giving us 18. Boom, parentheses are done. Now we drop back out to the rest of the sentence. 36 divided by 3 is 12. Finally, we just add our 2 simplified chunks together. 12 plus 18 gives us 30. By strictly following this grammatical rulebook of math, every single person who looks at that expression is going to arrive at exactly 30. No confusion.
All right, part 3, evaluating variables and expressions. It is officially time to introduce letters into our math language. These are called variables, and we're going to see how we can evaluate them by plugging in known numerical values. This is literally the moment arithmetic levels up into algebra.
This side-by-side comparison shows you exactly how we substitute those unknown letters with specific values. It turns a completely abstract algebraic expression back into a solvable numerical one. So on the left side, we've got 7x plus 5y plus 3. Now those x and y variables, think of them as just empty boxes waiting to be filled. The number sitting right next to the variable, like the 7 or the 5, is called a coefficient, and that just means multiply. So let's say we are told that x equals 8 and y equals 6. We just drop those numbers right into their boxes. The expression becomes 7 times 8 plus 5 times 6 plus 3. We bring back our handy order of operations, multiply to get 56 plus 30 plus 3, and evaluate the final answer to be 89. Pretty satisfying, right?
Okay, on to part 4, math shortcuts, operation properties. Every language on Earth has shortcuts and synonyms, right? Well, in algebra, these are our mathematical properties. They basically let us reorganize expressions without changing their core meaning or value.
Now keep in mind, these 4 properties only apply to addition and multiplication. but they give us the total freedom to legally move numbers around, which makes mental math unbelievably easy. First up, the commutative property. This means you can commute or move numbers around, like how 4 plus 6 is exactly the same as 6 plus 4. Then there's the associative property, which is all about who associates with whom. You can change where the parentheses are grouped. The identity property is literally about keeping your identity. Adding 0 or multiplying by 1 changes absolutely nothing. And lastly, the inverse property. Think of this as the undo button. Adding a negative version of a number gets you right back to 0.
So think about what we just learned for a second. If we change the expression 9 plus the group 5 plus 3 into the group 9 plus 5 plus 3, just to make it a little easier to add on our heads, which property did we just use? Are we changing the actual order of the numbers? Or are we just changing how they associate and group together? Look really closely at the numbers, 9, 5, 3. The order from left to right never changed at all. What changed was the parentheses. We shifted the grouping from the 5 and 3 over to the 9 and 5. Because we only changed who was associating with whom to make our mental math faster. 9 plus 5 is 14, plus 3 is 17. We successfully just used the associative property.
Section 5. Cleaning up, combining, and distributing. To make our mathematical sentences as concise and elegant as possible, we really need to learn how to clean up messy expressions. I mean, just like you wouldn't write, I have a cat, and I have a cat, and I have a cat, you definitely wouldn't leave a math sentence full of repetitive, clunky elements.
The absolute golden rule here is that you can only combine apples with apples. A term like 10x can absolutely be combined with a 5x, but there is no way you can combine it with a 2x squared. They might both have an x, but that little floating exponent makes them an entirely different species. Also, constants, which are just your plain old regular numbers like 10 and 7, those are like terms too, so they can be grouped together. So if you're faced with a messy expression, your whole job is to hunt down the identical variables, keep a close eye on the plus or minus sign in front of them, and combine them into a single clean package.
We can also clean things up using the distributive property, and this area model visualizes it perfectly. It proves how a number sitting outside the parentheses has to multiply with every single term hiding inside. Imagine a rectangle. The width of the whole shape is 2. The length is split into a part that's 6x and a part that's 12. Now to find the area of the entire shape, you multiply the width by the total length. You basically have to distribute or hand out that 2 to everything inside. So 2 times 6x gives us the blue area of 12x, and 2 times 12 gives us the green area of 24. It visually proves that 2 times the group of 6x plus 12 is exactly equivalent to 12x plus 24. It is such a fantastic visual shortcut.
And finally, part 6, translating the math language. For our final step in this explainer, we're going to bring all of these rules together and translate actual English sentences directly into algebraic code. This is the moment you become a true bilingual speaker of mathematics. By mapping specific English words like more than to addition and difference to subtraction, we can effortlessly translate verbal descriptions straight into mathematical expressions. For example, if you hear the phrase 8 more than a number, well, that number is an unknown, so we swap it for a variable like x. More than tells us we need to add. Put it together, and we write x plus 8. Or if we hear the difference of 10 and q, the word difference is a huge red flag signaling subtraction, so it perfectly translates to 10 minus q. You're really just playing detective, looking for the keyword synonyms for addition, subtraction, multiplication, and division.
So, I'll leave you with this takeaway challenge to test your brand new translation skills. Using everything we just covered, how would you translate the phrase, the sum of g and 11, into an algebraic expression? Look closely at the word sum to guide your operation. Identify your variable and put the whole shebang together. Once you can do that with confidence, you're not just solving math problems anymore. You are quite literally speaking the language of logic fluently. Thanks so much for joining me for this explainer, and keep practicing those expressions.